My presentation is potential vorticity mixing and rapid intensification in the simulated Supertyphoon Haiyan 2013. I will talk about the contribution of IOR-PV mixing to the central pressure drop during a tropical cyclone IR onset. First, tropical cyclone IOR dynamics still remain an open question. Some previous studies proposed important factors of strong boundary layer inflow and its associating large inward transport of absolute angular momentum, and also inner core convective bursts and warm core formation will be considered as other important factors. Associated with the tangential wind increasing during the storm RI, the central pressure is also rapidly decreasing. Then, how can the storm get the central pressure drop in the RI onset? We consider the IOR-PV mixing will be a key factor, which has been previously proposed in idealized simulations. Kossi and Schubert 2010 performed idealized simulations using an isentropic model and putting a PV ring at the initial time. This PV ring represents PV hollow tower due to the IOR convective heating. The initial PV ring destructed and a monopole PV structure formed at the final time. Associated with the PV redistribution, low-level air is warmed. This warming indicated formation or intensification of lower warm core and also central pressure drop. Our purpose is to quantitatively examine the contribution of the IOR-PV mixing to the storm central pressure drop around the RI onset. Particularly, we use model simulation for the real case in RI tropical cyclones to examine PV budget analysis and piecewise PV inversion. In the PV budget, we can quantitatively examine the PV change due to the PV mixing. In the piecewise PV inversion analysis, we can clarify the contribution of the PV mixing to the storm central pressure drop. Our target is the Supertyphoon Haiyan, which made landfall Philippines in 2013. In our previous work, non-hydrostatic model simulation with 2 km horizontal resolution, this simulation was performed. The bottom figure shows maximum wind speed estimation by JTWC, and also we show the model simulation. You can see that the simulation had delay of the RI onset about 2.5 days. On the other hand, the intensification rate is good agreement with the JTWC estimation. So we used the model results for 00Z to 06Z November 7. We focus on this period at around the RI onset. First, we show the PV evolution during the RI onset. This figure shows the potential vorticity in the numerical simulation using the color shading. At the RI onset, there are convective PV towers associated with an asymmetric IOR. The high PV value is gradually intruded to the storm center. So we use a PV budget analysis to quantitatively examine the PV increasing associated with the PV mixing processes. The budget equation contains axisymmetric and asymmetric PV advection, and also the equation contains the source or sink terms due to the diabatic heating and friction. The PV mixing is represented by the PV advection associated with the asymmetric flows. This is a result of the PV budget. It is actual change of PV and symmetric and asymmetric PV advection and diabatic heating and frictional contribution. You can see that the actual change near the storm center, the actual change of PV is dominated by the asymmetric PV advection. In this study, we focus on the contribution of the PV mixing to the central pressure drop during the RI onset. So we try to examine change of the pressure field associated with the PV tendency due to the asymmetric PV advection based on the PV budget results and also piecewise PV inversion technique. If we give any PV anomalies, we can diagnose the pressure and wind fields changed by the PV anomalies based on the inversion technique. Now, we have the change of the PV field in each term of the PV budget equations. So, we give the PV change in each term of the PV budget as the PV anomalies. After that, if we give the PV change due to the asymmetric PV advection in the PV anomalies, we can get the pressure change due to the asymmetric PV advection under the balanced state. This figure is the inversion results. Top is the actual change of geopotential height using contours. The maximum decrease is exhibited near the storm center. The value is about minus 80 meters. The middle figure is the geopotential height decrease by the actual PV change. The maximum decreasing is about minus 50 meters. This figure means the geopotential height decreasing under the balanced condition. The bottom is the geopotential height decrease by the asymmetric PV advection. The maximum decreasing is about minus 40 meters, which means that the balanced PV mixing accounts for about 50% of the total pressure drop at the storm center during the RI onset. Other balanced components account for about 15%. Other unbalanced processes account for about 35%. We discuss the relationship between the PV change in the free atmosphere and boundary layer flow. This figure shows the time series of rally of strong updraft and tangential wind, which is defined as mean rally of the top 2 percentile grids in the model simulation. After the PV budget analysis period, the strong updraft is located slightly inside of the radius of the maximum wind speed. This situation is in general agreement with observation studies during RI, for example, Rogers et al. 2013. The evolution suggests that the PV change and pressure drop above the boundary layer might be linked to the boundary layer through the radial pressure gradient force. I summarize this study. We focus on the central pressure drop associated with potential vorticity mixing between the eye and eye wall during the RI onset. Using non-hydrostatic simulation of Supertyphoon Haiyan 2013, we examined PV budget and the piecewise PV inversion diagnosis. The PV budget indicated that the dominant PV increasing in the eye due to the PV mixing. The piecewise PV inversion technique indicated that PV mixing can account for about 50% of the total pressure drop during the RI onset. Our results suggest that the PV change in the free atmosphere might be linked to the boundary layer inflow and updraft through the radial pressure gradient force. That's all. Thank you.